So I introduce next speaker, Sara Seager. She's a professor at MIT in various sciences, and she's pioneered many research areas in the exoplanetary science. And she is a PI of CubeSat, Asteria, and Deputy Science Director for TESS. And TESS will be launched on Monday, as she told me in the morning. She's lead also Starshade Rendezvous mission, and she's a member of U.S. National Academy and a MacArthur Fellow. Welcome.
Thank you. Okay, great. Well, I'm waiting for my slides here. I have something like brand new to tell you, and it comes about halfway through my talk. So until then, I just want to start with how I got onto this topic. And what happened was by the way, I work a lot on exoplanet atmospheres and the future search for biosignature gases. And one very amazingly astonishing thing I realized a few years ago, which is a fact but I hadn't read it anywhere, is that all gases in our Earth's atmosphere, to the part per trillion level, except for the noble gases, are actually produced by life. Now most of them have a dominant source that's not biotic. And there's about 30 or 40 gases, depending on how you count them, whether or not you include the human-made chlorofluorocarbons. So after that, and during that time, I was like, maybe life produces all gases. No, actually it doesn't, but that's what led me on this journey. And I recruited Janusz Petkowski, who's now a postdoc at MIT, and William Baines, who you just heard about in the last talk, to work on this project with me. Now in this image here, it's from Mauna Kea, showing you stars, beautiful starry night. And our stars can come in single stars or binary stars. You can see the Milky Way, the plane of the Milky Way there. There's some star clusters you can see. And our stars are bound in our Milky Way galaxy. And our galaxy is bound in a cluster. And we have a way of organizing our stars and our space. Well, in chemistry, we also there's a definition of chemical space. That's all the molecules, the properties of all the molecules and compounds that span a chemical space under a set of construction rules and boundary conditions. So this concept is foundational to drug discovery, for example, where in their computers, people will generate billions of molecules and then filter them in certain ways to try to use it. Well, we would each have our own path through chemical space. And I'm gonna start out by telling you a bit about biosignature gases before I get to my main topic. So here's the molecule of oxygen. Oxygens are still our favorite biosignature gas. And oxygen is so reactive, it shouldn't be in the atmosphere unless it's continually produced. But because I didn't see a lot of talks on exoplanets, so I'm giving you in a nutshell, all the latest work, just conceptually. There's this mini cottage industry now about all the different scenarios where oxygen could be produced abiotically, especially on planets in very different environments than our own Earth. But life on Earth, and the ones we're looking for on exoplanets, also include a lot of other small gases, like methane and nitrous oxide and other gases. And these gases are produced by microbes. They could be produced by simple single-celled life. But these gases, like methane and nitrous oxide, they're also going to have false positives because the life on Earth that makes these exploits chemical potential energy gradients. And they catalyze these gradients to make a reaction happen to get energy. But if life could catalyze these reactions, I can almost guarantee that there's another place on the planet, on Earth, where the temperatures and pressures make it so that that reaction could happen spontaneously. That's the same reaction happening, generating the same gas, like methanogenesis, for example. Life makes methane, but it's also produced at the mid-ocean ridges. Now, in addition to this list of small molecule gases, actually, there's other gases that exoplanet astronomers have studied for future biosignature observations. And these include methanol or dimethyl sulfide, that's not on here, or methyl chloride or other gases that they seem to have chosen somewhat randomly, that on other atmospheres that may not have a lot of oxygen or low ultraviolet environments from their host star could accumulate. But it turns out that these molecules are not from chemical energy gradients. They're produced for unspecified reasons, individually, maybe hormone signaling or stress or other things. And these gases are probably produced in really small quantities, but they might accumulate on environments different from Earth. It turns out that life on Earth produces thousands of molecules. And in my team, we actually have calculated literally every molecule that should be in gas form at Earth's temperature and pressure for CNOPSH. And we have our own algorithms to filter them, so we can try to sort through any biosignature gases. And here's a final stream of gases that are never made by life on Earth. So in this work, actually, that was kind of my entry into chemical space. And I just have a few notes there on the side that you can look at. But we, for some reason, we didn't really have a real purpose initially of curating this giant database where we scraped all databases almost that existed that were accessible. And this was mostly Janusz's work, and what I'll talk about from now on is his work. And we actually scraped databases. We did combinatorics to generate our own molecules in chemical space. And we now actually have a database of life's unique natural products that doesn't repeat any, and they're all uniquely, or they're all assigned to a certain species of life. Okay, so what's interesting about this was that in this database, we started to look for patterns of occurrence of different elements, bonds, and even molecular fragments and molecules. And what I'm showing here is a part of the periodic table, the P block, and if you can read it carefully, you can see the occurrence of different elements within our database. So for example, nitrogen, 24% about of all of these unique products made by life in our database is made by nitrogen. You can see sulfur around 3%. And so I don't know about you, but not for the chemists in the room, but let's say the astronomers or technologists, I would think that nitrogen-sulfur bonds would be quite common, at least maybe around 3%, like as much sulfur was used with life. But it turns out actually they're incredibly rare. And what we did was we actually have worked through the database, not actually totally, but there's many examples that people kind of already knew about but didn't really care about of these known gaps, puzzling gaps amidst the diversity of the chemistry of life. And here are just some examples. So nitrogen-sulfur bond containing compounds are very rare, as are nitrogen-nitrogen, and I list a bunch of others here, but I just wanted you to know that there are these patterns, these fragments that are very rarely or never produced by life. And the one I'm going to talk about today is the absence of a nitrogen-sulfur bond in biochemistry. So I'll leave it for you to judge whether it's, actually no, I won't. I would just tell you, it is amazing to me that only 100 molecules produced by life contain the nitrogen-sulfur bond, at least that are known. And this is out of more than 200,000 known unique products produced by life. That's 0.05%. The reason why I find it so incredible is that nitrogen-sulfur bond containing compounds are widely used in industry and medicine. So that leads to the question, why? Now on the right there, I'm showing you some molecules to emphasize the point that sulfur is unique because it has 3 different valence states. You can look at it, sulfur is the yellow in these pictures, 2 bonds, or it can have 4, or it can have 6. And this makes for a very rich, diverse chemistry. And so just to hit that point home of industry versus medicine, Janusz also compiled this chart, literally by combing databases for all molecules used in industry and medicine that have the nitrogen-sulfur bond. And if you look on the y-axis, you'll see hundreds, numbers go up to hundreds. For those tall bars, those are compounds in industry, up to thousands even. And life produces very few. You can hardly see them in comparison. And they're divided into these different structural types based on the number of bonds. So, okay, the motivation is just that given the scope of chemical space, why did life choose the path it did? And why did it avoid certain chemical functionalities? Okay, I just want to briefly say that most people don't like this approach, actually. And there are biochemists who have focused on cherry-picked examples of why life does certain things, but not why life doesn't do things. So I'm going to give you the hypothesis, and then I have a few slides supporting the hypothesis. So this hypothesis is that nitrogen-sulfur chemistry is incompatible with life's biochemistry. Specifically, that it is very reactive to a very common compounds with the functional group SH, sulfur hydrogen group, thiols. They're called thiols, are sulfur hydrogen group containing compounds that are basically foundational to biochemistry. So what this means is if we went to another planet where life had chosen to use NS bond containing compounds and not thiols because of the reactivity, if we went there, we would literally, I want to say, be poisoned on the spot. And we would also be poisoning all that other life. Now, one of the main criticisms, I'm just going to say the criticism so the people in the room who would have it won't say it. You don't have to say it if I have time to say it. It's just that some people go, no, we already understand how life does things. Life has certain limited building blocks, and in our bodies it's aqueous, so that's limiting, and oxygen environment and all that. But honestly, no, it really doesn't apply here because nitrogen and sulfur compounds are literally everywhere as building blocks. In terms of these medicine and industry, many of them are made for aqueous environments, and an oxygen environment isn't really also really important for it. So now I'm going to give you the support for the hypothesis. I didn't say proof here, it's just support. And in this next slide, you don't have to read those molecules. They're just there for people who know what they are and can read them. But it's showing you in red in the colors on the left the numbers of compounds in different nitrogen-sulfur, these structural classes. So NS2 would be sulfur with 2 bonds, 4 with 4, 6 has 6 bonds. And this colorful arrow, the colorful arrow, is showing you the reactivity with thiol. So these extremely rare ones are incredibly reactive with thiols. Like in the presence of thiols, it's like seconds. And less reactive as you go down towards the bottom. And this reactivity, we got these rates mostly from the literature. And they weren't papers on this reactivity. They're kind of very buried. Papers that were on other things where authors would say, oh, wow, we noticed this is a very reactive set of compounds. And I just wanted to say one thing about, and also this reactivity doesn't match, this reactivity pattern doesn't match with other common functional groups. I just want to say something about this S6 at the bottom. It's still a very small number, but a relatively major fraction of all of these nitrogen-sulfur compounds. They're still very rare. Most of them look like they're toxic. It's probably their toxicity or their biosynthetic pathway that makes them so rare, because if they involve any of the other products or breakdown products or need those ones to form, then they'll be reactive as well. Now, this evidence provides support that thiol reactivity is to blame because the occurrence matches with the reactivity. So to take this a step further and to make sure that we did some of our own experiments. Actually, I'm an astrophysicist, not a biochemist, and Janusz doesn't have his own lab, so we actually contracted out we found a local company called Organics, and we asked them to do the experiments for us. And what we did was we chose a set of 7 sugars and amino acids as proxies for metabolites, and we made it so that each of them contains a functional group used in biology and cell biology. So we wanted to make sure that when we test our reactions, it'd be pretty clear what was going on by having simple molecules with distinctive functional groups. And we did, they did an NMR, nuclear magnetic resonance time course reactivity assay. And it's kind of hard to tell what's going on here, but there's 4 different, this isn't everything, but these are 4 we're showing you. Oops, now I went, seeing if I have a laser here. Okay, basically blue is time equals 0, and orange is at 24 hours. So you're looking to see if there's a difference between blue and orange. If there's a difference, it means a reaction happened and the compound broke up. If it's the same, nothing happened. And the compounds we're showing you are shown up here. So this is an NS2, the 2 bonds, and we had 2 different ones just in case one didn't work, and they both show reactions with L-cysteine, which is the only one in our set of 7 that has the thiol group. So it reacted. And then we also tested the NS6 to show that it didn't react. So we just kind of, in combination with literature results, it provides support for this idea that thiol reactivity is to blame, and that nitrogen-sulfur compounds nitrogen-sulfur bond-containing compounds are avoided by life on Earth. So the summary is that we propose this incompatibility. And perhaps non-Earth-like life could have taken a different path, favoring nitrogen-sulfur bond-containing chemistry and not thiols. We don't know for sure yet, but there may be other mutually exclusive sets of chemical options leading to islands of biochemistry. And in my team, led by Janusz, this is the first part of a larger effort in pattern recognition. And by the way, this whole work that I told you in the database and figuring all of this out in the experiments, that was like years of work, actually. So it's not necessarily easy. We just worked on the one that we could find a solution for first. So thank you for your attention. And here's the 3, I forgot to mention one thing. For these 100 compounds that life does make that have the nitrogen-sulfur bond, Janusz wrote a paper. There's actually a Journal of Natural Products. Natural products are products produced by life. And every single compound in there he's now written about. And it's like a review article of where it comes from, like what kind of life makes it and what its biosynthesis pathway is. And then we have all the work I talked about is currently under review at astrobiology. Thank you.
Thanks. That's really cool. It sounds like this may be the seeds of an approach which allows us to identify what we might think of as anti-biosignatures, chemicals, gases, and atmospheres whose presence is incompatible, at least with certain kinds of life.
Okay, it's possible. It may be, yeah, that's a good question. It may be incompatible with our life, but maybe it's going to be compatible with the life that's there. Right.
One more.
Thanks. The cysteine is super important for really stable proteins, right, with the disulfides. Is there a thing there where we couldn't have these stable proteins if we were making these gases because it would just react with them and destroy them? Do you think that's what's going on here, or is it more general than that?
Can you repeat that, please?
Disulfide bridges, which stabilize proteins, are one of the reasons, if you will, for cysteine, I think, right? So in order to have stable proteins, you've got to have these sulfur-containing amino acids, but that would then all be undone if these toxic gases were being produced. Do you think that's are you saying that's what's going on here, or is there a more general reason why these?
Like, I can't answer your question specifically.
Okay.
But I just think it's the NS compounds reaction with thiols. I should be able to answer that one about disulfide, but I can't.